All right, so hello and welcome to another Math 5 video. Today we are going to review a little bit on exponential functions and logarithmic functions. Everything from today's video is going to come from our textbook, sections 4.2 to 4.4. And in this video, the intention is just to go over the problems on the worksheet or the concepts that are on the worksheet. I won't be doing the problems on the worksheet itself, but problems similar to those that are in the textbook. And we're going to go through this fairly quickly, just to show how the problems are done. And if you want more detail, I have a longer video that goes over, in detail, logarithmic and exponential equations. Okay, so feel free to watch that video. This video is intended to be short. I'll try to keep it as short as I can and do as much as I can. Okay, so let's go ahead and jump into problem number 1 on the worksheet. And problem number 1 is on rewriting exponential and log equations. And so it gives us a log equation. Let's use log base b of x equals y. And this is equivalent to, so this is what we call logarithmic form. We can rewrite this in a similar or an equivalent form as b to the y equals x. So if you want to imagine, that y, changes place with x, x goes to the other side of the equal sign, and then the b kind of just enlarges. So we get b to the y equals x. So we have that kind of, if you want to use that as a little device to try to remember that. And so this gives us a way to write logarithmic equations in exponential form. And so here is a problem from the textbook. Log base 2 of 8 equals 3. So this is in log form or logarithmic form. But so what does this mean? What the log base 2 of 8 is the exponent that I need to put on 2 to get 8. And we know that that's 3. So that's why log base 2 of 8 is equal to 3. So in log form, we can rewrite this. And let's see, if we switch the 8 and the 3, we would get 2 to the third equals 8, right? And I think we're more familiar with that equation there. This is the same equation or an equivalent equation, but now we've written it in exponential form. Okay. All right. So here is another one. How about log base 3 of 9 equals 2? Right? And you can pause the video anytime I write a problem down and try to do it yourself. This is going to be the base to the exponent equals 9. And so here we know that this is true. Clearly, 3 to the second power is 9. So then this equation, since it's equivalent, is also true. The exponent that I put on 3 to get 9 is 2. Okay? So that's how that can be read. What exponent do I put on 3 to get 9? That's the number 2. All right, let's do one more. Log base 7 of 1/7 equals -1. So before I write that -1, you could have actually answered this yourself and ask yourself, what exponent do I need to put on 7 to get 1/7? And 7 and 1/7 are reciprocals of each other, so we need a negative exponent. So this can be written as 7 to the -1 equals 1/7 if I flip those things around. So 7 to the -1 is 1/7. And if you remember your rules of exponents, that is correct. Okay, so let's switch from that. We've done essentially these problems there, or you can do those now on your own. And let's go ahead and switch into writing them using exponential form and then rewriting them in logarithmic form. Okay, so Let's do, how about 5 squared equals 25. This is a true statement. It's an exponential form. I can now rewrite this as log with a base of 5. That's the base of the exponential of 25 equals 2. The exponent I put on 5 to get 25 is 2. Okay. How about another one? How about 9 to the 0 equals 1? The base of the exponential expression is 9, so that's going to be the base of the log. And then we do that little switching action. So the 1 would be on the other side of the equal sign, same as the 9 equals 0 goes to the other side. Log base 9 of 1 equals 0. And so hopefully you're remembering these rules also, that basically any number to the 0 raised to the 0 power is equal to 1. All right, and then the last one, 81 raised to the 1/2 power equals 9. If you remember 81 to the 1/2, that's the same as the square root, the second root of 81. And we know that that's 9. So 81 to the 1/2 equals 9. The log with the base of 81 of 9 is equal to, so what exponent do I put on 81 to get 9? That is 1/2. Okay. Very good. Now I'll cover one more thing here because I can see in the worksheet that it covers the irrational number e. So let me take a moment to just mention that one. Let's say e to the, we'll do e to the 1/3 equals the cube root of e. E is just a special number like pi. Pi is approximately equal to 3.1415. E is approximately 2.71828. Okay, so it's one of those, just like pi is a number that comes up in, natural applications, the number e is very important as well. And if we rewrite this in logarithmic form, we would get log with a base of e of the cube root of e equals the exponent, which is 1/3. And so let me continue to talk about the log with the base of e. We've already seen a few logs already, log base 2, log base 3, log base 7. And the log, remember, is just a way of describing the exponent that goes on the base that gets you the number that's inside the parentheses in the argument. Okay, so logs can have different bases, just like exponential expressions can have different bases. So there is one log that's it comes up often enough where we give it a special notation, and that is a log with a base of e. The log with the base of e may be written as the natural log, ln. So I can write the expression log base e of the cube root of e as ln of the cube root of e equals 1/3. Okay. So you have to recognize that if you see ln, that can just be rewritten as log with a base of e. And then you go from that logarithmic form and rewrite it in its exponential form. So I just wanted to spend a little bit more time there talking about log base e. We'll talk about it some more. But essentially, we've covered all of the material on problem number 1. Cool. How much time do we have there? 10 minutes. Whoa. Okay. On problem number 2 talks about the log properties. And just like we have properties with exponential expressions like x squared times x to the fifth, hopefully you remember that that is x to the seventh power, right? You add the exponents to get your final expression there. We add the exponents when we multiply. So notice that multiplication of two exponential expressions ends up requiring us to do some addition. And so we have similar properties with logs. If you add log base b of m plus log base b of n, the sum of these two logs turns out to be a log with a base of b of m times n. So it's kind of like the reverse of the exponential expressions, because exponential expressions and log expressions they're inverses of each other. And so notice that an addition is carried out through some sort of multiplication. So addition of two logs is equal to the log of the product of the arguments. Okay, and then similarly, log base b of m minus log base b of n is equal to the log base b of m divided by n. Okay, that shouldn't be too much of a surprise. If addition gives you multiplication, it makes sense that subtraction will give you division. So we'll just call this number 1, call this number 2. And then the third and final property that that's on this problem number 2 is when you have the log base b of, what do they call it there? I'm just going to call it m to the r. There is a property where if a log is applied to an exponential expression, you can take that exponent and bring it out to the front and write it as r times log base b of m. Okay. So we'll just make up a couple of problems similar to those that are in problem number 2, since this actually didn't show up in the textbook in exactly the same way. So in problem number 2, let's see. Let's say we want log base 3 of 12 plus log base 3 of blank, some blank thing there. And this is equal to log base 3 of 36, right? So what must that be? If I add two logs, I need to multiply the arguments. So I'd have to multiply 12 by this number to get 36. And we know that 12 times 3 is 36. So our answer must be, that blank spot must be 3. Okay. How about log? Let's see, which was the one that confuses people? Yeah, log base. This one's similar to part F in problem number 2. Log base 5 of, let's say, of 9 equals blank times log base 5 of 3. Well, let's see. It doesn't look like there's a sum of logs, or a difference of logs. So we can write this as log base 5. This is probably going to be property number 3. And we know that 9 is 3 squared. So using property number 3, that allows us to pull a 2 outside. And so log base 5 of 9 is equal to 2 times log base 5 of 3. That is our blank spot. And then we'll do one. Let's do one more. Similar to E, let's say. We'll make it a little bit different, but log base 5 of 27 minus log base 5 of blank equals log base 5 of 9. Okay, well, we know when we subtract two logs, that means to divide the two arguments. So whatever goes in here, I'm going to put an X for right now. These two logs would combine to be log base 5 of 27 divided by X. And if this is equal to log base 5 of 9, then 27 over X must be equal to 9. So 27 divided by what number is 9? We can see that that's 3. So X equals 3. You might be able to see that right away without writing all this out. If you can, then good for you. You can just plug it in there. That empty spot there is 3. Okay, problem number 3 just goes over, let's see here. Problem number 3 talks about y equals the natural log of x. It says that y equals natural log of x is it's called the natural logarithmic function. And it says it has a base of e, which again is approximately 2.71828. Now, I skipped one there in the first part. Y equals, there's also a log that doesn't have a base written. That's just called is a common logarithmic function. It's called the common log. And it has a base of 10. If you ever see, just like we said, the natural log of x can be written as log base e of x. The log of x can be written as log base 10 of x. Okay. So basically that's the answer to number 3, since there's no other way to say it. That's in our textbook. All right. And now let's go ahead and jump on to problem number 5, which talks about the domain of logarithmic functions. And so let's see here. Did we have some 73, from 73 to 78 in our textbook? Was similar. So let's go ahead and just take one from the textbook, and I'll modify it a little bit. Y equals the log of, let's start with x plus 3. I'm not going to go into the details. You can watch my other video if you want to see that. But if you want to find the domain of a log function, and actually, let me make you wait just another moment. I will write another problem here. Y equals 2x cubed plus the log of, and let's do 3 minus 2x. Okay, so here's another problem. Just like I did 2 of them, I'll do them very quickly. The domain of a logarithmic function is where this inside part, sometimes called the argument of the log, we set that argument greater than 0. You may remember when we did the square root functions, square root of 2x plus 10 or something like that, that we would do the argument 2x plus 10, or called the radicand, greater than or equal to 0. That's slightly different. We're not dealing with radical functions anymore, but it's very similar in the sense that we set the argument greater than, greater than 0. And so now all we do is solve for x. This one's easy, subtract 3. And x is greater than -3. So in interval notation, that would be all numbers greater than -3. We do not include the end value of -3, so we use parentheses. So it is very important. Let's do the next one, that we write our inequality. The argument 3 minus 2x greater than 0, not equal to, just greater than. And then we solve for x. We'll subtract 3. A few people actually messed this up on the quiz, so that's why I'm writing the inequality. Some people put equals, and sometimes when you write the equals sign, you can kind of make a mistake, because when you divide by a negative, if you write the inequality, hopefully you'll remember that whenever you divide an inequality by a negative, you need to flip the inequality symbol. If you have an equal sign, you might not notice that, and you might just, if you flip an equal sign, it's still an equal sign. So we get the negatives cancel, and we get 3 halves. X is less than 3 halves. And so the domain is negative infinity, all numbers less than 3 halves to 3 halves, not including 3 halves. And sometimes people ask, well, what about this 2x cubed? Does that do anything? And the answer is no, because this is a polynomial term, and this does not make any sort of restriction to the domain of the function. The restrictions that we have so far come from, well, now log functions, the argument must be greater than 0, or radical functions, where the argument must be greater than or equal to 0, or rational functions, x plus 5 over, 5x plus 15 or something, where there the denominator cannot equal 0. Okay, so there I'm kind of saying a little bit extra, but just to kind of tie it back to something we've done in the past. Okay, so that's problem number 5 done there. Let's go back to problem number 4, solving logarithmic equations. So it's good that we skipped number 4 for a moment, and then now we're coming back to it, because we're going to solve logarithmic equations in problem number 4, and then some more in problem number 6, and then some more in problem number 7. All right. So, I'm doing a little bit of explanation here, but notice we're 22 minutes in, and, we've done roughly half of the problems on this worksheet. All right. Problem number 4. Okay. So we'll just make some up. I don't think I found any good ones in the textbook, but let's say the log base 5 of 5 equals x. So with these logarithmic equations, one way that we could try to solve these is to rewrite them in their exponential form. The base, and if we switch these, raised to the x equals 5. 5 raised to what exponent is equal to 5? Well, we all know that 5 to the first power is 5, so x must be equal to 1. Okay. And again, you could actually even probably just figure it out just by looking at this logarithmic equation. If you understand what a log means, it just means the exponent that you put on this little 5 to get that 5, to get that argument. And the exponent would be 1, so x must be equal to 1. Oops. Uh-oh, my pencil died. Okay. Let's see if it's dead. Okay. Yes. So let me go ahead and charge my pencil here just for a moment, and then we can talk a little bit about, we can just keep this going and talk about the next problem. So let's see here. That's a little unfortunate. Let's see. In the meantime, maybe you can think of the next problem. I'll go back into the worksheet. If you write this problem down, the log base 2 of 1/8 equals x. That would be similar to part C on problem number 4. The log base 2 of 1/8. And let's see here. I'm at 4% now. Let's give it a try again. See if this comes back. Resume.